Picture yourself standing on a beach in ancient Greece, 2400 years ago. The Mediterranean stretches endlessly before you, its waves carrying ships from distant lands. You watch rivers flowing steadily into this vast body of water. The Nile, the Danube, countless smaller streams all pouring their contents into the sea. A question forms in your mind, the same question that puzzled Aristotle. Why doesn't the ocean overflow? Day after day, year after year, rivers dump enormous volumes of water into the sea, yet the water level never rises. The shoreline remains constant. Where does all that water go? Aristotle pondered this mystery, proposed theories, but the answer eluded him. It would take 2,000 years, 2 millennia of human questioning, before we understood the water cycle, before we grasped how evaporation and precipitation work together in an endless dance of transformation. This is where wonder meets the unknown. In that space between question and answer, between curiosity and understanding, humanity has always lived. We exist in a universe that seems designed to perplex us, where every solved mystery births 10 new riddles, where each answer illuminates vast territories of ignorance we never knew existed. Here's what's really happening when we encounter the unknown. Our brains, those pattern-seeking machines evolution crafted over millions of years, collide with phenomena that refuse to fit our categories. The result is that peculiar sensation we call wonder, part confusion, part delight, part urgent need to understand. It's the feeling that drove ancient peoples to create stories about gods hurling lightning bolts, the same feeling that drives modern physicists to peer into particle accelerators searching for the building blocks of reality. Consider Isaac Newton, arguably the most brilliant mind in human history, sitting beneath an apple tree in 1665. The plague had closed Cambridge University, sending him home to contemplate the natural world. When that apple fell, and yes, this actually happened, though probably not directly onto his head, Newton experienced a moment of profound wonder. Here was something so ordinary, so everyday, that most people never questioned it. Things fall down. But Newton asked, why? His mathematical genius allowed him to describe gravity with stunning precision. He could calculate the exact path of a cannonball, predict the return of Halley's comet, explain the tides. Yet Newton himself called gravity an absurdity. He could describe how it worked, but not why. How could massive objects exert forces across empty space? How could the Earth pull on the Moon across 239,000 miles of apparent nothingness? Newton wrote to his colleague Richard Bentley that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, without the mediation of anything else, is to me so great an absurdity that I believe no man who has, in philosophical matters, a competent faculty of thinking can ever fall into it. The man who gave us universal gravitation found his own discovery absurd. This wasn't false modesty. It was honest recognition that solving one mystery had revealed an even deeper puzzle. Newton had answered the how of gravity, but left the why completely untouched. It would take Einstein's general relativity, 250 years later, to show us that massive objects actually bend the fabric of space and time itself. But here's the beautiful irony. Einstein's answer, brilliant as it was, immediately spawned new mysteries. If space and time are curved, what exactly is being curved? What is the underlying structure of reality? We're still asking these questions today, still standing at the edge of the known world, still feeling that same wonder Newton felt beneath his apple tree. This pattern repeats throughout human history. In 1896, Marie Curie discovered that uranium salts could expose photographic plates even in complete darkness. Here was matter spontaneously emitting energy, apparently violating the fundamental law of energy conservation. Her radium glowed eerily in the dark, challenging everything science thought it knew about the stability of atoms. The scientific establishment initially resisted her findings. Energy cannot be created or destroyed, this was physics gospel. Yet here was undeniable evidence of matter spontaneously radiating energy. Curie's mysterious substances were literally glowing contradictions to established law. Her discovery didn't just solve a puzzle, it shattered the puzzle box itself. Radioactivity forced scientists to completely reimagine the atom, leading to quantum mechanics, nuclear physics, and ultimately our modern understanding of stellar fusion. The stars themselves, it turned out, were powered by the same radioactive processes Curie observed in her laboratory. But follow this thread of discovery, and you'll find it leads directly to today's mysteries. Curie's work helped us understand how stars shine, yet now we know that ordinary matter, the stuff of stars and planets and people, makes up less than 5% of the universe. The other 95% remains completely mysterious. Dark matter and dark energy, invisible forces that shape cosmic evolution yet leave no trace in our detectors. We exist in a universe where the vast majority of reality is hidden from us. This isn't a temporary gap in knowledge, it's a fundamental challenge to our understanding of existence itself. We've gone from not knowing why the ocean doesn't overflow to discovering that most of the ocean is invisible. Here's what's truly remarkable about human curiosity. It operates across every timescale imaginable. Aboriginal Australians preserved geological knowledge in their Dreamtime stories for 60,000 years, far longer than written history. Their oral traditions describe landscapes that existed before the last ice age, encoding information about sea level changes, volcanic eruptions, and terrain features in mythological narratives that served as both entertainment and data storage. These weren't primitive people making up stories about rocks. They were sophisticated observers, creating memory systems that preserved accurate information across more than 2,000 generations. Western science is only now recognizing the geological accuracy embedded in these ancient narratives. Stories about the rainbow serpent carving river valleys correspond precisely to periods of massive flooding. Tales of islands disappearing match sea level rise from melting glaciers. The same curiosity that drove Aboriginal storytellers drives today's researchers at the edge of the observable universe. When we look at the stars, we're looking back in time. The light hitting your eyes began its journey years, decades, even centuries ago. The most distant galaxies we observe existed when the universe was young, their light travelling for over 13 billion years to reach us. But here's where it gets truly mind-bending. We can only see a tiny fraction of what exists. The observable universe, everything we can possibly detect, extends about 46 billion light-years in every direction. Beyond that horizon lies... what? More galaxies? Different physics? Something utterly alien to our experience? We don't know. We can't know. The expansion of space itself ensures that light from beyond this boundary will never reach us. We exist inside a cosmic bubble of knowledge, surrounded by infinite mystery. This should be terrifying. Instead, for many of us, it's exhilarating. We've gone from wondering why the sea doesn't overflow to discovering that we live in an island of light surrounded by an ocean of darkness. The scale of our ignorance has expanded dramatically, yet somehow this makes the journey more exciting, not more depressing. Here's what's actually happening when we push against the boundaries of knowledge. We're not just satisfying curiosity, we're defining what it means to be human. No other species asks questions about the fundamental nature of reality. No other creature looks at a falling apple and wonders about the structure of space and time. This capacity for wonder, this compulsion to understand, appears to be uniquely ours. When early humans first looked up at the night sky and invented constellations, they weren't just organizing random dots of light. They were taking the first steps toward astronomy, toward navigation, toward eventually leaving Earth itself. Those star patterns guided Polynesian voyagers across thousands of miles of open ocean. They helped ancient farmers know when to plant crops. They inspired calendars, mathematics, and ultimately space travel. The same stars that puzzled our ancestors now serve as cosmic laboratories. We've learned to read their light like books, discovering their composition, their age, their fate. A single spectrum of starlight tells us more about distant suns than ancient astronomers could learn about our own. Yet every answer reveals new questions. We now know that stars form in vast molecular clouds, that planets condense from leftover debris, that life might be common throughout the cosmos. But we still don't know why anything exists at all. Why is there something rather than nothing? Why does the universe seem fine-tuned for complexity, for stars, for planets, for life, for consciousness? These aren't just abstract philosophical puzzles, they're driving practical research. Scientists are building ever more sophisticated telescopes, particle accelerators, and detection systems, searching for answers that might revolutionize our understanding of existence. The James Webb Space Telescope can peer deeper into space and time than ever before, potentially observing the very first stars and galaxies. The Large Hadron Collider recreates conditions from moments after the Big Bang, searching for new particles and forces. We stand at an extraordinary moment in human history. For the first time, our technology allows us to probe the deepest mysteries of reality directly. We can observe black holes swallowing stars, detect gravitational waves from colliding neutron stars, and manipulate individual atoms with laser light. Yet, the more precisely we can measure the universe, the stranger it becomes. Quantum mechanics tells us that particles exist in multiple states simultaneously until observed. Einstein's relativity shows us that time and space are fluid, changeable. Modern cosmology reveals that the universe emerged from a point smaller than a proton and somehow grew to contain billions of galaxies. These aren't just scientific theories, they're invitations to fundamentally reimagine the nature of reality. The journey from Aristotle's overflowing ocean to today's dark energy involves more than accumulating facts. It represents the evolution of human consciousness itself. We've learned to ask better questions, to design more clever experiments, to think in ways that transcend common sense. We've developed mathematics that describes patterns spanning from subatomic particles to galactic clusters. We've created instruments that extend our senses across the electromagnetic spectrum and beyond. But perhaps most importantly, we've learned to embrace uncertainty. The greatest scientific minds don't claim to have all the answers. They're the ones asking the most profound questions. They stand at the boundary between known and unknown, between comprehension and mystery, and find joy in the journey rather than frustration at the destination's elusiveness. When you look up at the night sky tonight, you're participating in humanity's oldest and newest adventure. You're seeing photons that began their journey before your species existed, carrying information about cosmic events unfolding on scales that dwarf imagination. You're also confronting the same fundamental mysteries that puzzled ancient philosophers and continue to challenge modern physicists. The ocean doesn't overflow because water evaporates and falls as rain, completing a cycle Aristotle couldn't see. But why does water behave this way? Why do molecules dance between liquid and gas? Why does energy flow spontaneously from hot to cold, driving weather patterns and ultimately life itself? Each answer opens new vistas of wonder. This is where we live permanently suspended between question and answer, between the known and the unknowable. It's a peculiarly human space, this realm of wonder. We alone among Earth's creatures seem compelled to understand not just how to survive, but why we exist at all. The universe has presented us with an infinite curriculum, and we've barely begun our studies. Every answered question reveals how much we don't know. Every solved mystery illuminates vast territories of ignorance we never suspected existed. This isn't a flaw in human knowledge, it's the engine of human progress. From this moment forward, We'll explore some of these territories together. We'll venture into the earliest moments of life on Earth, when chemistry first crossed the threshold into biology. We'll journey inside consciousness itself, where billions of neurons create the miracle of awareness. We'll confront the dark forces that shape cosmic evolution and learn to read Earth's climate diary written in ancient ice. Each destination will reveal new wonders, new mysteries, new questions that future generations will struggle to answer. This is the nature of the human journey. We exist at the edge of knowledge, always reaching toward understanding, never quite arriving but finding meaning in the search itself. The universe seems designed to keep us wondering, to ensure that every answer births new questions, that every solved puzzle reveals deeper mysteries. Whether this is cosmic purpose or cosmic accident, we may never know. But we can know this. In our capacity for wonder, in our compulsion to understand, in our willingness to embrace both knowledge and mystery, we've found something uniquely valuable in the cosmos. We are the universe's way of wondering about itself. In our questions, reality becomes self-aware. In our search for answers, existence finds meaning. The journey from Aristotle's overflowing ocean to tomorrow's discoveries isn't just scientific progress. It's consciousness itself, learning to comprehend the incomprehensible, one beautiful mystery at a time. 4 billion years ago, Earth was an alien world. The sky glowed orange-red from methane and ammonia. Lightning crackled almost continuously through the thick atmosphere. Volcanic eruptions painted the horizon with rivers of molten rock. And somewhere in this hellscape, in pools of water no bigger than puddles, chemistry crossed an invisible threshold into biology. We weren't there to witness this moment, of course. No one was. Life's first spark occurred in absolute solitude, with no observers except perhaps the indifferent stars. Yet somehow, against all odds, in a universe that seemed hostile to complexity, molecules began to dance in patterns that would eventually lead to consciousness, to art, to the very questions we're exploring together. Here's what's truly remarkable about this transformation. It happened not once, but potentially countless times across billions of years. Life didn't emerge through a single miraculous event, but through countless experiments in chemistry, most of which failed, leaving no trace. We exist because of the survivors, the molecular arrangements that discovered how to persist, how to copy themselves, how to evolve. In 1953, a graduate student named Stanley Miller decided to recreate Earth's ancient atmosphere in his laboratory. Picture this: glass flasks connected by tubes, filled with methane, ammonia, hydrogen, and water, vapor, electric sparks simulating lightning, a simple setup that would revolutionize our understanding of life's origins. Miller sealed his primordial atmosphere inside the apparatus and let artificial lightning discharge through it for a week. When he analyzed the results, he found something extraordinary: amino acids. The building blocks of proteins had formed spontaneously from simple gases and electricity. Life's ingredients could emerge from lifeless chemistry. The implications hit the scientific community like a thunderbolt. For centuries, many believed life required some special vital force, some divine spark to animate dead matter. Miller's experiment suggested otherwise. Given the right conditions, the right chemicals, the right energy source, life's components assemble themselves. But here's where the story gets even more fascinating. Miller's original atmosphere, methane, ammonia, hydrogen, probably wasn't accurate. Earth's early atmosphere likely contained more carbon dioxide and nitrogen. When scientists repeated the experiment with updated atmospheric compositions, they still got organic compounds, but different ones. Life, it seems, can emerge through multiple pathways. This tells us something profound about the universe we inhabit. Life isn't a fragile accident that happened once on one planet. It appears to be what scientists call an emergent property, something that naturally arises when energy flows through complex chemical systems. Under the right conditions, chemistry seems almost eager to become biology. To truly understand this transformation, we need to journey to some of Earth's most extreme environments. 3,000 feet beneath the Pacific Ocean, where crushing pressure and scalding heat should make life impossible, entire ecosystems thrive around hydrothermal vents. Here, water reaches 700 degrees Fahrenheit, hot enough to melt zinc yet remains liquid due to immense pressure. These underwater volcanoes spew chemicals that would be toxic to most surface life: hydrogen sulfide, methane, heavy metals. Yet around these hellish fountains, life explodes in forms that rewrite biology's rules. Bacteria consume rocks, extracting energy from chemical bonds instead of sunlight. Shrimp with no eyes navigate by sensing infrared heat. Tube worms, the size of baseball bats, have no mouth, no gut, no obvious way to eat, yet they thrive by hosting colonies of chemosynthetic bacteria in their tissues. When scientists first discovered these vent ecosystems in 1977, it was like finding aliens on our own planet. Everything we thought we knew about life's requirements, sunlight, moderate temperatures, familiar chemistry, proved wrong. Life had found ways to extract energy from the Earth itself, creating ecosystems that could survive even if the sun went out. Here's what's really happening at these vents. We're seeing evolution experiment with the most fundamental question of existence. How do you build order from chaos? How do you create complexity from simplicity? The organisms around hydrothermal vents represent billions of years of chemical innovation, life forms that discovered how to harvest energy from geological processes. These discoveries force scientists to expand their definition of habitability. If life can thrive in boiling, toxic, lightless environments on Earth, where else might it exist? The ice-covered moons of Jupiter and Saturn suddenly became potential oases. Mars, with its subsurface water and geological activity, transformed from a dead rock into a possible cradle of biology. But to understand how life first emerged, we need to travel to Western Australia's Pilbara region, where some of Earth's oldest rocks preserve fossils from 3.5 billion years ago. Here, in formations with names like Strelley Pool and Dresser, you can touch stones that contain the earliest known evidence of life. These aren't fossils in the traditional sense, no bones or shells or leaves. Instead, we find stromatolites, layered rock structures built by ancient microbial mats. Picture billions of bacteria living together in thin films, trapping sediment and minerals as they grow. Over time, these microbial communities create distinctive layered patterns, like living geological formations. The remarkable thing about stromatolites is that they're still being built today. In Shark Bay, Western Australia, microbial mats continue constructing these living rocks using the same processes that operated billions of years ago. You can walk along the shoreline and observe structures identical to the oldest fossils on Earth. It's like stepping back in time, witnessing biology as it existed when our planet was young. These modern stromatolites teach us something crucial about early life. The bacteria building them aren't complex organisms with sophisticated cellular machinery. They're simple, ancient forms of life that have remained virtually unchanged for billions of years. Yet they're capable of transforming their environment on a planetary scale. Here's what those early microbes accomplished. They invented photosynthesis. For the first 2 billion years of Earth's history, the atmosphere contained virtually no oxygen. Then, cyanobacteria, blue-green algae, began using sunlight to split water molecules, releasing oxygen as waste. This might seem like a minor chemical innovation, but it transformed the entire planet. The Great Oxidation Event, as scientists call it, was actually a catastrophe for early life. Oxygen was poison to the anaerobic organisms that had dominated Earth for billions of years. It was the first extinction crisis, caused not by asteroids or volcanoes, but by life itself. Yet this crisis also created opportunities. Oxygen-breathing organisms could extract far more energy from their food, enabling the evolution of complex cells, multicellular life, and eventually consciousness. We exist because ancient bacteria polluted their atmosphere with a toxic waste product that happened to be useful for more sophisticated forms of life. The oxygen you're breathing right now is the accumulated exhaust of countless microbial generations stretching back billions of years. But how did life cross that initial threshold from chemistry to biology? This question has puzzled scientists for decades, but recent discoveries are providing fascinating clues. In laboratories around the world, researchers have found that life's building blocks can assemble spontaneously under surprisingly simple conditions. When fatty acids, simple organic molecules, encounter water, they automatically form tiny spheres called vesicles. These aren't random blobs. They're organized structures with distinct inside and outside regions, primitive cell membranes that can grow, divide, and even compete for resources. No DNA required, no complex machinery needed, just chemistry following the laws of physics. Even more remarkably, these protocells can evolve. When researchers create populations of vesicles with slightly different compositions, some grow faster than others. The successful variants eventually dominate the population. It's natural selection operating on purely chemical systems, evolution without biology. Here's what this means. The transition from non-life to life might not require a miraculous leap. Instead, it could be a gradual slope where chemistry slowly becomes more complex, more organized, more lifelike. The boundary between living and non-living might be blurrier than we ever imagined. This research is revealing something profound about the universe we inhabit. Life doesn't appear to be a rare accident that happened once on one planet. Instead, it seems to be what emerges naturally when energy flows through complex chemical systems. Given enough time and the right conditions, matter organizes itself into increasingly sophisticated patterns. Scientists call this process emergent complexity. Simple rules, operating over long periods, can generate behaviors and structures that seem impossibly sophisticated. It's the same principle that allows flocks of birds to perform aerial ballet without a choreographer, that enables markets to set prices without central planning, that permits brains to generate consciousness from the interactions of mindless neurons. The implications are staggering. If life emerges naturally from chemistry, then every planet with liquid water and energy sources becomes a potential biological laboratory. The universe might be teeming with experiments in complexity, with countless worlds where matter is learning to organize itself into living systems. Recent discoveries have expanded this possibility even further. Scientists have found organic compounds in meteorites, suggesting that life's building blocks form naturally in space. Observations of distant star systems reveal complex organic molecules in the cosmic dust surrounding young stars. Even comets contain amino acids and other biological precursors. This means the ingredients for life are being distributed throughout the galaxy by cosmic processes. Every solar system receives a delivery of organic compounds from interstellar space. The raw materials for biology appear to be ubiquitous in the cosmos. But here's where the story becomes even more extraordinary. Life on Earth didn't just emerge once and then remain static. It continuously reinvents itself, discovering new ways to extract energy, new strategies for survival, new forms of complexity. The tree of life is really more like a vast web, with organisms constantly sharing genetic information, merging, splitting, exploring new ecological niches. Consider the endosymbiotic theory, one of biology's most elegant insights. The complex cells that make up plants, animals, and fungi didn't evolve gradually from simple bacteria. Instead, they formed through mergers. Ancient bacteria engulfed other bacteria, and instead of digesting them, learned to live together. The mitochondria that power your cells were once free-living bacteria. The chloroplasts that enable photosynthesis in plants were originally independent cyanobacteria. Life, it turns out, evolves not just through competition, but through cooperation. Organisms that learn to work together can access new energy sources, survive in new environments, achieve new levels of complexity. Your own body is really a colony of trillions of organisms working in harmony, not just human cells, but bacteria, archaea, and other microbes that help you digest food, fight infections, and maintain health. This realization transforms our understanding of what it means to be alive. You're not a single organism, but an ecosystem, a walking community of life forms that have learned to cooperate so intimately that they function as a unified whole. The boundary between self and environment, between individual and community, dissolves under careful examination. Recent research in astrobiology, the search for life beyond Earth, suggests that similar cooperative strategies might be operating throughout the cosmos. If life emerges naturally from chemistry, and if cooperation drives increasing complexity, then the universe might be full of biological communities we can barely imagine. The search for extraterrestrial life has shifted from looking for little green men to seeking signatures of biological processes. Scientists scan the atmospheres of distant planets for oxygen, methane, and other gases that life produces. They listen for radio signals that might indicate technological civilizations. They design missions to drill beneath the ice of Europa and Enceladus, searching for microbes in alien oceans. But perhaps the most profound search is the one happening right here on Earth, in laboratories where scientists are trying to create life from scratch. By assembling synthetic genomes, building artificial cells, designing novel biochemistries, researchers are learning what life requires and how it might emerge elsewhere in the universe. These experiments reveal that life is both more fragile and more robust than we might expect. It requires specific conditions, liquid water, energy sources, organic compounds, but within those constraints, it displays remarkable creativity. Life finds ways to thrive in environments that seem impossibly hostile, to extract energy from sources that seem unlikely, to organize matter in patterns of breathtaking complexity. The story that began 4 billion years ago in tiny pools of water continues today in every cell of your body. The same chemical processes that first crossed the threshold from chemistry to biology are still operating, still creating order from chaos, still building complexity from simplicity. You are not separate from this process, you are this process, temporarily organized into a pattern complex enough to contemplate its own existence. When you breathe, you're participating in chemical cycles that connect you to every other living thing on Earth and to the ancient atmosphere created by countless microbial generations. When you think, you're experiencing the universe, becoming aware of itself through biological processes that emerged from simple chemistry. When you wonder about life's origins, you're extending the same curiosity that drove those first self-replicating molecules to explore new possibilities. Life's first spark in the cosmic dark wasn't a single event but an ongoing process. It's happening now, in your cells, in laboratories around the world, and potentially on countless worlds throughout the universe. We exist because chemistry learned to remember, to copy itself, to evolve. And that learning continues, carrying life toward forms of complexity we can barely imagine. The universe began as a cosmic soup of hydrogen and helium. Through billions of years of stellar fusion, gravity, and chemical evolution, it has organized itself into galaxies, stars, planets, and life. We are the cosmos learning to understand itself, one discovery at a time. The spark that ignited in those ancient pools hasn't gone out. It's grown into the light of consciousness, illuminating the darkness with the warmth of awareness, the glow of wonder, the fire of endless possibility. Inside your skull, at this very moment, 86 billion neurons are firing in patterns more complex than all the stars in the Milky Way. These aren't just random electrical sparks, they're orchestrated symphonies of information, cascading waves of activity that somehow, through mechanisms we barely understand, create the entire universe of your inner experience. Think about what's happening as you read these words. Light patterns on a screen trigger chemical changes in your retina. Those changes become electrical signals racing along your optic nerve at 200 miles per hour. Within milliseconds, millions of neurons across dozens of brain regions activate in precise coordination, transforming meaningless photons into meaningful thoughts, emotions, memories, and understanding. You're not just processing these words, you're experiencing them. There's something it's like to understand a sentence, to feel curiosity about consciousness, to wonder about the nature of your own mind. This inner experience, this subjective awareness, represents one of the deepest mysteries in all of science. How does the activity of mindless neurons create the felt experience of being you? Neuroscientist Christoph Koch has offered $1 million to anyone who can solve what philosophers call the hard problem of consciousness. It's not enough to explain how the brain processes information, stores memories, or controls behavior. The hard problem asks why there's an inner experience at all. Why do we have subjective awareness, rather than simply behaving like sophisticated biological robots? Consider the redness you experience when looking at a rose. Your brain can measure the wavelength of light approximately 700 nanometers. It can track how this information travels through your visual system, activates specific neural circuits, triggers memories and emotions. But none of this explains why you experience redness as redness. Why isn't the processing of 700 nanometer light simply dark and computational, like the operation of a computer? Why is there this vivid, immediate, unmistakable quality of red experience? This isn't just an abstract philosophical puzzle. It touches the very foundation of what it means to be human. Every emotion you feel, every memory you cherish, every moment of beauty or pain or joy, all of it emerges somehow from the electrical activity of neurons. Yet the gap between brain activity and conscious experience seems as vast as the space between Earth and the most distant galaxies. To understand this mystery, we need to journey into some of the strangest territories of neuroscience. In the 1960s, surgeons began treating severe epilepsy by cutting the corpus callosum, the thick bundle of nerve fibers connecting the brain's two hemispheres. This procedure, called corpus callosotomy, often reduced seizures dramatically, but it also created something unprecedented: people with literally divided minds. These split-brain patients appeared normal in most situations. They could walk, talk, perform complex tasks. But careful testing revealed something disturbing. The two hemispheres of their brains were no longer communicating, creating what seemed like two separate streams of consciousness within a single skull. Watch what happens when researchers show a split-brain patient two different images simultaneously, one to each hemisphere. A picture of a spoon appears in the left visual field, processed by the right hemisphere. A picture of a fork appears in the right visual field, processed by the left hemisphere, which controls speech. When asked what they saw, the patient says, "Fork," that's the verbal left hemisphere responding. But when asked to point with their left hand, controlled by the right hemisphere, to what they saw, they point to the spoon. Two different answers from the same person, because the person has become, in some sense, two different people. Even more unsettling, sometimes the two hemispheres actively conflict. The left hand literally fights the right hand, a condition called alien hand syndrome. One hemisphere might try to get dressed while the other attempts to undress. One might reach for an object while the other pushes it away. The unified self we take for granted proves to be a construction, vulnerable to disruption. Here's what this tells us about consciousness. It's not a single, indivisible thing. Your sense of being a unified self emerges from the constant chatter between different brain regions, each contributing its own specialized processing. Cut those connections, and the illusion of unity dissolves, revealing consciousness as what it really is, a democracy of competing processes that usually reach consensus but sometimes erupt in civil war. This insight becomes even more profound when we examine how normal brains construct the sense of self. Your prefrontal cortex creates narratives about your experiences, weaving memories and perceptions into coherent stories. Your temporal lobes form and retrieve memories, providing the continuity that makes you feel like the same person over time. Your parietal cortex integrates sensory information to create your sense of body ownership, the feeling that your hands belong to you, that your thoughts originate from inside your head. But all of these processes can be disrupted independently. Stroke patients sometimes develop conditions like hemispatial neglect, where they lose awareness of one side of space. They might eat only the food on the right side of their plate, shave only the right side of their face, deny that their left arm belongs to them. Their consciousness hasn't disappeared, it's been edited, revealing that awareness is more like a construction project than a fundamental property. Even stranger, some patients develop blindsight after damage to their visual cortex. They claim to be completely blind in certain regions of their visual field, yet they can catch balls thrown at them, navigate around obstacles, even guess the emotional expressions on faces they insist they cannot see. Their brains are processing visual information and using it to guide behavior, but consciousness has been stripped away from the process. This reveals something startling about awareness. Most of what your brain does happens unconsciously. The vast majority of neural processing, recognizing faces, controlling movement, regulating heartbeat, maintaining balance, occurs without any conscious experience whatsoever. Consciousness appears to be like the tip of an iceberg, a tiny visible portion of mental activity floating above an enormous invisible foundation. But if consciousness is such a small part of mental life, why does it exist at all? What evolutionary advantage does subjective experience provide? This question has sparked fierce debates among scientists and philosophers. Some argue that consciousness is necessary for flexible behavior, allowing organisms to integrate information from multiple sources and plan for future scenarios. Others suggest it's an emergent property of complex information processing, arising naturally when neural networks reach a certain level of sophistication. One of the most intriguing discoveries in recent neuroscience is mirror neurons, brain cells, that fire both when you perform an action and when you observe someone else performing the same action. These neurons, first discovered in macaque monkeys, create empathy at the cellular level. When you watch someone reach for a cup, neurons in your premotor cortex fire as if you were reaching for the cup. In yourself, this neural mirroring might be the foundation of social consciousness. By simulating others' actions in our own brains, we can predict their intentions, understand their emotions, share their experiences. The phrase, "I feel your pain," turns out to be neurologically literal. Watching someone suffer activates the same brain regions involved in experiencing pain yourself. Here's what's remarkable about this discovery. It suggests consciousness isn't just individual, but fundamentally social. Your sense of self develops through constant interaction with other minds. You learn to recognize your own thoughts by first learning to recognize thoughts in others. Consciousness emerges not from isolated brains, but from brains in communication, creating shared spaces of experience that transcend individual skulls. This social dimension of consciousness becomes vivid when we examine what happens during sleep. As you drift off each night, your brain doesn't simply shut down, it shifts into a different mode of operation. The logical prefrontal cortex reduces its activity, while the emotional limbic system runs wild, generating experiences that feel completely real despite defying the laws of physics. In dreams, you can fly, breathe underwater, converse with the dead, or find yourself naked in high school 20 years after graduation. The brain creates these bizarre narratives by randomly accessing memory fragments and weaving them into stories that seem perfectly sensible while you're experiencing them. Only upon waking do you realize how impossible it all was. Dreams reveal something profound about consciousness. It's not a passive receiver of information, but an active constructor of reality. Your brain is constantly creating models of the world, filling in gaps, making predictions, generating the seamless experience of awareness. Most of the time, these models closely match external reality. But in dreams, the model-making machinery operates without external constraints, creating experiences that are phenomenologically real but factually impossible. Recent research using brain imaging has revealed that consciousness operates through what scientists call global workspace dynamics. When information becomes conscious, it's literally broadcast throughout the brain, becoming available to multiple processing systems simultaneously. Unconscious processing tends to be local and specialized, specific brain regions handling specific tasks, but conscious processing integrates information across the entire nervous system. This integration happens through synchronized neural oscillations, brain waves that coordinate activity across distant regions. When you become aware of something, neurons across your brain begin firing in rhythm, creating a temporary coalition of consciousness. The experience of unified awareness emerges from this neural synchrony, this moment when your entire brain speaks with one voice. But here's where the mystery deepens. We can measure these neural correlates of consciousness, but we still can't explain why they feel like anything. Why should synchronized neural firing create the experience of seeing red or feeling pain or understanding a joke? The gap between objective neural activity and subjective conscious experience remains as puzzling as ever. Some researchers propose that consciousness might be a fundamental feature of the universe, like mass or electric charge. Just as electrons have a certain charge, perhaps matter has a certain degree of consciousness. This view, called panpsychism, suggests that subjective experience exists at all levels of reality, from individual particles to complex brains. Human consciousness would then be what emerges when billions of micro-conscious entities organize themselves into sophisticated networks. This might sound absurd, but it addresses a real problem in consciousness research. If consciousness emerges from unconscious matter, there must be some threshold where subjective experience suddenly appears. But this seems as mysterious as claiming that wetness suddenly emerges from dry molecules or that life suddenly emerges from dead chemistry. Perhaps consciousness, like these other emergent properties, is really about organization rather than the emergence of something genuinely new. Other scientists take a different approach, focusing on the functions consciousness serves rather than its subjective qualities. They study how conscious processing differs from unconscious processing, what cognitive advantages awareness provides, how consciousness might have evolved through natural selection. This approach has revealed that consciousness excels at integrating information from multiple sources, creating mental models of possible futures, and enabling flexible responses to novel situations. For instance, conscious processing allows you to hold multiple possibilities in mind simultaneously. When deciding whether to take an umbrella, you can mentally simulate different weather scenarios, consider the consequences of each choice, and select the option that best serves your goals. This kind of counterfactual thinking, imagining what might happen under different circumstances, seems to require conscious awareness. Consciousness also enables what psychologists call metacognition, thinking about thinking. Right now, you can not only read these words but also monitor your own comprehension. Notice when you're confused. Decide whether to reread a paragraph. This self-awareness allows for sophisticated learning strategies, error correction, and cognitive control. But perhaps the most remarkable feature of consciousness is its creativity. The same neural machinery that creates dreams also generates insights, innovations, and artistic visions. When you have a sudden aha, the moment when you see unexpected connections between ideas, when you experience beauty or wonder, these are consciousness operating at its most sophisticated level, integrating information in novel ways that can surprise even yourself. Recent studies of psychedelic experiences provide another window into consciousness. Drugs like psilocybin and LSD dramatically alter brain activity, reducing communication between different neural networks while increasing activity within individual networks. This creates profound changes in conscious experience. The dissolution of the sense of self, synesthesia, where senses blur together, mystical experiences of unity with the universe. These chemically altered states suggest that ordinary consciousness is just one possible configuration of brain activity. The default network that usually maintains your sense of self can be temporarily disrupted, creating experiences that feel more real than ordinary reality. Many people report that psychedelic experiences fundamentally change their understanding of consciousness and reality, providing first-hand evidence that awareness is far more malleable than we typically assume. The study of consciousness also intersects with artificial intelligence in fascinating ways. As we build increasingly sophisticated computer systems, we're forced to confront the question, could machines become conscious? Current AI systems can process information, recognize patterns, even generate creative outputs, but there's no evidence they experience anything subjectively. However, some researchers argue that consciousness might emerge naturally from sufficiently complex information processing systems. If consciousness is really about integration, communication, and self-modeling, then advanced AI systems might spontaneously develop some form of awareness. This possibility raises profound ethical questions about the rights and moral status of artificial minds. The architecture of awareness reveals itself to be both more complex and more fragile than our everyday experience suggests. Consciousness isn't a thing, but a process, not a place, but a pattern, of activity, not a possession, but a performance. It emerges from the dance of neurons, but can't be reduced to neural firing. It creates the experience of being you, while remaining, paradoxically, impersonal in its mechanisms. Every moment of awareness represents a minor miracle. Billions of neurons achieving temporary consensus about the nature of reality, creating a unified experience from chaotic activity, generating the inner life that makes existence meaningful rather than merely mechanical. You are consciousness examining itself, awareness becoming aware of awareness, the universe developing the capacity to wonder about its own nature. The mystery persists, as deep and puzzling as ever. Why should there be something it's like to be you? Why should the electrochemical activity of neurons feel like anything at all? These questions may never receive complete answers, but in the asking, in the wondering, in the very experience of being puzzled by our own existence, we encounter something precious, consciousness, contemplating itself, mind marveling at mind, awareness amazed by the simple fact of awareness itself. In 1933, Swiss astronomer Fritz Zwicky aimed his telescope at the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity, 290 million light-years from Earth. What he observed shouldn't have been possible. The galaxies were moving so fast they should have escaped each other's gravitational pull billions of years ago, scattered across the cosmos like marbles thrown from a moving car. Yet there they were, dancing together in gravitational harmony, despite moving at impossible speeds. Zwicky realized that invisible hands must be holding them together, some form of matter that didn't shine, didn't emit light, didn't reveal itself through any telescope. He called it Dunkel Materie, dark matter. It was the first glimpse of what we now know to be the universe's greatest secret. Today, we understand that dark matter outweighs visible matter by 5 to 1. Everything you can see, every star, planet, nebula, and galaxy, represents less than 5% of the universe's total mass and energy. The cosmos is dominated by invisible forces that reveal themselves only through their gravitational effects, like ghosts moving furniture in a haunted house. Here's what's truly unsettling about this discovery. Trillions of dark matter particles are streaming through your body right now as you read these words. They pass through you, through Earth, through the Sun without leaving the slightest trace. You're being continuously bombarded by invisible matter that outweighs your atoms 5-1, yet you feel nothing. It's as if we exist in a shadow universe, aware only of the tiny luminous fraction, while remaining blind to the vast dark majority. The evidence for this invisible matter is overwhelming and comes from multiple independent observations. In the 1970s, astronomer Vera Rubin studied the rotation of spiral galaxies and discovered something that should have overturned Newton's laws of gravity. Stars at the outer edges of galaxies were orbiting just as fast as those near the center, when they should have been moving much more slowly. Picture our solar system for comparison. Mercury, closest to the Sun, races around its orbit at 47 kilometers per second. Earth, farther out, moves at 30 kilometers per second. Neptune, at the system's edge, crawls along at just 5 kilometers per second. The farther from the gravitational center, the slower the orbital speed, exactly what Newton's laws predict. But galaxies don't follow this pattern. Stars at their outer edges maintain speeds that should fling them into intergalactic space. It's like discovering that the outer planets in our solar system are somehow orbiting as fast as Mercury without being pulled into the Sun. The only explanation: these galaxies must be wrapped in cocoons of invisible mass, dark matter halos that extend far beyond the visible stars. The implications hit cosmology like an earthquake. Either our understanding of gravity, tested successfully from laboratory experiments to planetary orbits, breaks down on galactic scales, or the universe contains vast quantities of matter we've never detected. Most scientists chose to accept the existence of dark matter rather than abandon Newton and Einstein. But dark matter is just the beginning of the cosmic mystery. In 1998, two competing teams of astronomers made a discovery that shook the foundations of physics. They were studying distant supernovae, exploding stars that serve as cosmic lighthouses, their brightness indicating their distance from Earth. What they found defied every prediction about the universe's fate. The expansion of space itself was accelerating, not slowing down as gravity pulled everything back together, but speeding up, as if some mysterious force was pushing galaxies apart. The teams checked and rechecked their data, searched for errors, questioned their methods, but the evidence was undeniable. The universe was not just expanding, but expanding faster and faster with each passing moment. This discovery revealed the existence of dark energy, a force even more mysterious than dark matter. While dark matter at least behaves like matter, clustering around galaxies and affecting their rotation, dark energy appears to be a property of space itself. The more space expands, the more dark energy there is, driving ever faster expansion in an accelerating feedback loop. Dark energy represents approximately 68% of the universe's total mass energy. Dark matter accounts for another 27%. Everything we can see, all the stars, planets, gas and dust, makes up just 5%. We exist as a tiny visible minority in a cosmos dominated by forces we can barely detect, let alone understand. Here's what's happening on the largest scales. Dark energy is winning a cosmic tug-of-war with gravity. For the first few billion years after the Big Bang, gravity dominated, slowing the expansion of space as matter clumped together to form stars and galaxies. But as space expanded and matter became more diffuse, dark energy's influence grew stronger. About 7 billion years ago, dark energy took control, and cosmic expansion began accelerating. This has profound implications for the universe's future. If dark energy continues to dominate, galaxies will fly apart until each exists in complete isolation. Stars will exhaust their fuel and burn out, leaving behind cold remnants in an ever-expanding, ever-cooling cosmos. The universe will end not in a fiery big crunch, but in a big freeze, approaching absolute zero temperature as it expands toward infinity. But how do we study forces that leave no direct trace? Scientists have developed ingenious methods to detect the invisible. Gravitational lensing reveals dark matter through its effect on light from distant galaxies. Massive concentrations of dark matter bend space-time, causing light to curve around them like water flowing around rocks in a stream. When astronomers observe distant galaxies through galaxy clusters, they sometimes see multiple images of the same object, distorted into arcs and rings by the gravitational lensing effect of intervening dark matter. These cosmic mirages allow us to map the distribution of invisible matter with remarkable precision, revealing how dark matter forms the scaffolding upon which visible matter builds galaxies. Computer simulations of cosmic evolution show dark matter forming a vast web of filaments, connecting dense nodes where galaxies eventually form. This cosmic web structure matches exactly what we observe in the distribution of galaxies across the sky. Visible matter simply follows the invisible architecture that dark matter creates. Even more remarkably, scientists have learned to detect dark energy through its effects on the cosmic microwave background, the afterglow of the Big Bang itself. Tiny temperature fluctuations in this primordial light encode information about the universe's composition and geometry. The pattern of these fluctuations can only be explained by a cosmos dominated by dark energy and dark matter in precisely the proportions we observe today. The search for dark matter has spawned one of the largest experimental programs in physics. Deep underground laboratories shield sensitive detectors from cosmic rays, hoping to catch the rare collision of a dark matter particle with atomic nuclei. The Large Hadron Collider smashes protons together at nearly light speed, searching for new particles that might explain dark matter's nature. Space-based telescopes hunt for the signatures of dark matter annihilation, the possibility that these invisible particles occasionally destroy each other, producing gamma rays or other detectable radiation. So far, despite decades of searching and billions of dollars invested, dark matter particles remain maddeningly elusive. This elusiveness has led some scientists to propose alternatives to the dark matter hypothesis. Modified theories of gravity suggest that perhaps our understanding of gravitational forces breaks down on cosmic scales. Maybe there's no invisible matter at all, just gravitational effects we don't yet comprehend. But these alternative theories struggle to explain all the observations that dark matter accounts for so elegantly. The cosmic microwave background, gravitational lensing, galaxy rotation curves, and large-scale structure formation all point consistently toward invisible matter that interacts gravitationally, but not electromagnetically. Dark matter remains the leading explanation despite its mysterious nature. The mystery deepens when we consider what dark matter might actually be. Leading candidates include WIMPs, weakly interacting massive particles that were created in the early universe, but interact so weakly with ordinary matter that they're nearly impossible to detect. Other possibilities include axions, sterile neutrinos, or entirely new classes of particles beyond the standard model of physics. Some theories suggest dark matter might exist in a dark sector, a parallel physics with its own particles and forces that interact with our world only through gravity. There might be dark atoms, dark molecules, even dark planets and dark stars made of matter that remains forever invisible to us. We could be sharing space with an entire shadow universe that operates according to different rules. Dark energy presents even greater puzzles. The most straightforward explanation links it to quantum mechanics' prediction that empty space isn't truly empty but filled with virtual particles constantly popping into and out of existence. This quantum vacuum should exert pressure, potentially driving cosmic expansion. But when physicists calculate the expected strength of this quantum vacuum energy, they get an answer that's wrong by 120 orders of magnitude, the largest discrepancy between theory and observation in the history of science. Either our understanding of quantum mechanics is fundamentally flawed, or dark energy has a completely different origin. Alternative explanations for dark energy include quintessence, a dynamic field that permeates space and changes over time, or modifications to Einstein's general relativity that become significant only on cosmic scales. Some theories propose that dark energy isn't constant but evolves as the universe ages, potentially leading to cycles of expansion and contraction. The study of dark forces has revealed something profound about the cosmos. The universe is far stranger and more complex than anything our ancestors could have imagined. We live in a reality where most of existence remains hidden from our senses, where invisible forces shape the largest structures in nature, where the very fabric of space-time is accelerating toward an unknown destiny. Recent observations have added new layers to the mystery. The collision of neutron stars detected by gravitational wave observatories has provided independent measurements of cosmic expansion rates that don't quite match values derived from the cosmic microwave background. This Hubble tension suggests either measurement errors or new physics beyond our current understanding. Gravitational waves themselves represent a revolutionary new tool for studying dark forces. When black holes or neutron stars spiral into each other, they create ripples in space-time that travel at light speed, carrying information about cosmic events happening billions of light-years away. The detection of these waves by LIGO and Virgo observatories opens entirely new windows into the universe's hidden dynamics. The waves LIGO detected from colliding black holes involved objects weighing 30 times more than our Sun, spinning around each other at a significant fraction of light speed, before merging into a single, larger black hole. The gravitational waves from this collision compressed and stretched space itself by distances smaller than 1/10,000th of the width of a proton. Yet our instruments detected them across 1 billion light-years of space. Here's what's truly remarkable. Gravitational waves are predicted to interact with dark matter in specific ways. Future observations might reveal how these mysterious particles respond to passing gravitational radiation, providing the first direct probe of dark matter's properties beyond its gravitational effects. The search for dark matter has also revealed the limitations of human sensory experience. We evolved to detect electromagnetic radiation, light, heat, radio waves, because these forms of energy could help our ancestors find food, avoid predators, and navigate their environment. But the universe contains forms of matter and energy that don't interact electromagnetically at all. This means our most sophisticated instruments, optical telescopes, radio dishes, X-ray detectors, are blind to the cosmic majority. We're like creatures that can only see in one narrow slice of the electromagnetic spectrum, trying to understand a universe painted in colors we cannot perceive. The fact that we've detected dark matter and dark energy at all represents a triumph of human ingenuity over sensory limitations. At underground facilities around the world, scientists maintain vigils for dark matter's rare interactions with ordinary matter. These experiments must shield their detectors from every possible source of interference: cosmic rays, radioactive decay, even the natural radioactivity in the human body. Some detectors are so sensitive they can register the recoil of a single atomic nucleus struck by a dark matter particle. The dedication required for these experiments is extraordinary. Scientists sometimes wait years for enough data to draw meaningful conclusions. They must account for every possible source of background noise, every way their detectors might produce false signals. Yet they persist, driven by the knowledge that the first direct detection of dark matter would revolutionize our understanding of the cosmos. Meanwhile, the Large Hadron Collider continues its search for new physics by recreating conditions from moments after the Big Bang. When protons collide at 99.99% of light speed, the tremendous energies involved can create exotic particles that existed naturally only in the early universe. Among these might be the particles that make up dark matter. Each collision produces showers of particles that sophisticated detectors track with incredible precision. Scientists search for missing energy cases where the total energy going into a collision doesn't match the energy of detected particles coming out. This missing energy might indicate the creation of dark matter particles that escape the detector without leaving a trace. The implications of dark matter and dark energy extend far beyond academic physics. They suggest that human knowledge, impressive as it seems, captures only a tiny fraction of reality. We've built telescopes that peer to the edge of the observable universe, particle accelerators that recreate the first moments of time, yet we remain ignorant of 95% of existence. This cosmic humility is both unsettling and inspiring. It reminds us how much remains to be discovered, how many mysteries await future generations of scientists. The universe has surprised us before with relativity, quantum mechanics, and the expanding cosmos, and it will surely surprise us again as we continue probing the nature of dark forces. Perhaps most importantly, the study of invisible matter and energy reveals the power of human reasoning to transcend sensory limitations. We cannot see, touch, or directly detect dark matter and dark energy, yet we've deduced their existence through careful observation and mathematical analysis. This represents one of the greatest intellectual achievements in human history, discovering the invisible through pure thought. The dark forces shaping everything operate on scales that dwarf human experience, yet they influence the very existence of galaxies, stars, and planets. Without dark matter's gravitational scaffolding, galaxies would never have formed. Without dark energy's accelerating expansion, the universe's geometry and ultimate fate would be completely different. We exist because of invisible forces we're only beginning to understand. As you sit here reading these words, trillions of dark matter particles stream through your body each second, carrying information about the universe's hidden architecture. Dark energy slowly stretches the space around you, contributing to cosmic expansion that will ultimately determine whether distant galaxies remain visible to future astronomers or disappear beyond the horizon of observability. The cosmos reveals itself to be not a place but a process, not a thing but a dynamic system where invisible forces sculpt visible structures across billions of years. We participate in this process not as observers but as participants, made of atoms forged in stellar furnaces, organized by forces we're still learning to detect, temporary patterns in the vast dance of matter, energy, space, and time. The dark forces shaping everything remain largely mysterious, but their discovery has already transformed our understanding of existence itself. We live in a universe far stranger, more complex, and more magnificent than previous generations could have imagined. And this is likely just the beginning, the first glimpses of cosmic truths that will continue revealing themselves to minds curious enough to keep searching, patient enough to keep watching, bold enough to accept that reality exceeds our wildest dreams. Number Chapter 5, Earth's Climate Memory. Written in ice, deep beneath Antarctica's frozen surface, where the temperature never rises above -40 degrees Fahrenheit, and the ice stretches 3 miles thick, scientists drill through time itself. Each core they extract contains layers of ice laid down year by year, season by season, preserving ancient atmospheres in tiny bubbles like messages in bottles from Earth's distant past. The deepest cores reach back 800,000 years, each annual layer a page in Earth's climate diary. Trapped within these frozen archives are samples of ancient air, volcanic ash from eruptions that darkened skies for years, dust from continental deserts blown across oceans, even traces of cosmic debris from asteroid impacts. Every snowflake that fell and compressed into ice has become a witness to history. Here's what's remarkable about these ice archives. They reveal that Earth's climate is far more dynamic and unstable than human experience suggests. The relatively stable conditions of the past 10,000 years, the entire span of human civilization, represent an unusually calm period in our planet's tumultuous climate history. For most of the past million years, Earth has been a wildly different world, When scientists analyze the carbon dioxide trapped in ancient ice, they find a pattern that remained virtually unchanged for hundreds of thousands of years. During ice ages, atmospheric carbon dioxide levels dropped to around 200 parts per million. During warm interglacial periods, they rose to about 280 parts per million. This rhythm, low during cold periods, higher during warm ones, played out across countless cycles as ice sheets advanced and retreated. Then came the Industrial Revolution. Starting around 1850, carbon dioxide levels began climbing beyond anything seen in the ice record. The concentration shot past 300 parts per million in the 1950, through 400 parts per million in 2014, and continues rising today. In just 2 centuries, human activity has pushed atmospheric carbon dioxide to levels not seen for over 3 million years. But the ice cores reveal something even more unsettling than rising greenhouse gas concentrations: evidence that Earth's climate can flip between dramatically different states in mere decades. Scientists studying Greenland ice discovered something called Dansgaard-Oeschger events, moments when regional temperatures jumped 18 degrees Fahrenheit in as little as 10 years. Picture this: a climate transition equivalent to shifting from Boston's weather to Atlanta's, happening not over centuries but within a single generation. Tree lines moved hundreds of miles. Ice sheets advanced or retreated with startling speed. Ocean currents reorganized themselves across entire basins. These weren't gradual changes, but rapid reorganizations of the entire climate system. The most dramatic example occurred about 12,800 years ago, just as Earth was emerging from the last ice age. Temperatures in the North Atlantic region had been warming steadily for several thousand years, when suddenly, within a few decades, ice age conditions returned. This event, called the Younger Dryas, plunged much of the northern hemisphere back into a 1,000-year-long deep freeze. Here's what apparently triggered this climate flip. The massive ice sheets covering North America began melting as global temperatures warmed. Enormous volumes of fresh water poured into the North Atlantic, disrupting the ocean circulation system that carries warm water from the tropics toward the poles. When this circulation shut down, Europe and eastern North America rapidly returned to ice age conditions, despite continued warming in other parts of the world. The Younger Dryas demonstrates something crucial about Earth's climate. It operates like a complex system with multiple stable states. Small changes can sometimes trigger large reorganizations, pushing the climate from one equilibrium to another. It's like a marble rolling around in a landscape of hills and valleys. Most of the time, it settles into stable positions, but occasionally it gains enough energy to roll over a ridge into an entirely different valley. This insight has profound implications for understanding modern climate change. The gradual warming we observe might seem manageable, but the ice cores warn us that gradual changes can trigger abrupt transitions. The climate system has tipping points, thresholds, beyond which change becomes self-reinforcing and potentially irreversible. To understand how these tipping points work, we need to examine the intricate machinery of Earth's climate system. Our planet's temperature depends on a delicate balance between incoming solar energy and outgoing heat radiation. This balance is modified by an elaborate network of feedback loops involving ice, clouds, vegetation, and ocean currents. Consider the ice albedo feedback loop. Ice and snow reflect sunlight back to space, keeping surfaces cool. But when warming melts ice, it exposes darker surfaces that absorb more heat, causing additional warming and more melting. This positive feedback can amplify small temperature changes into large ones, potentially triggering rapid ice sheet collapse. The Arctic Ocean demonstrates this process in real time. As global temperatures rise, Arctic sea ice melts, exposing dark ocean water that absorbs heat instead of reflecting it. This additional heat absorption accelerates warming in the Arctic, melting more ice in an accelerating cycle. Arctic temperatures are rising twice as fast as the global average. a phenomenon scientists call Arctic amplification. But ice sheets aren't the only component of the climate system capable of dramatic change. Ocean circulation plays an equally crucial role in determining regional climates. The Gulf Stream, for instance, carries as much heat northward as 1 million power plants, warming Europe by approximately 18 degrees Fahrenheit compared to similar latitudes in North America. This ocean heat transport depends on what oceanographers call the thermohaline circulation, a global conveyor belt of currents driven by differences in water temperature and salinity. Warm, salty water from the tropics flows northward along the surface, cooling and becoming denser as it travels. Eventually, this dense water sinks and flows back southward along the ocean bottom, completing a circulation pattern that spans entire ocean basins. The ice cores reveal that this circulation system has shut down repeatedly throughout Earth's history, often in response to fresh water inputs from melting ice sheets. When the circulation slows or stops, heat transport between latitudes is disrupted, causing rapid cooling in some regions and warming in others. The results can be dramatic. Ice Age conditions returning to Europe while tropical regions continue warming. Recent observations suggest that the Atlantic circulation is already slowing due to increased freshwater input from melting Greenland ice. Climate models predict further weakening as warming accelerates ice sheet melting. While a complete shutdown seems unlikely in the near future, even a partial slowdown could significantly alter weather patterns across the North Atlantic region. The ice cores also preserve evidence of another crucial climate component: volcanic eruptions. When volcanoes inject sulfur compounds into the stratosphere, they create aerosol particles that reflect sunlight and cool global temperatures. The ice captures this volcanic debris, allowing scientists to correlate specific eruptions with climate changes. The 1815 eruption of Mount Tambora in Indonesia demonstrates volcanism's climate impact. The ice cores show massive sulfur deposition following the eruption, coinciding with what historians call the year without a summer. Crop failures across Europe and North America caused widespread famine, while abnormal weather patterns persisted for several years. More recently, the 1991 eruption of Mount Pinatubo in the Philippines temporarily cooled global temperatures by about 1 degree Fahrenheit for 2 years. This cooling effect was precisely predicted by climate models, providing strong validation of our understanding of how aerosols affect Earth's energy balance. But natural climate variability extends far beyond volcanic eruptions and ocean circulation changes. The ice cores reveal complex interactions between solar cycles, atmospheric chemistry, and biological processes that create climate patterns on timescales ranging from years to millennia. The El Niño Southern Oscillation, for example, redistributes heat across the Pacific Ocean every few years, affecting weather patterns worldwide. During El Niño events, warm water spreads eastward across the Pacific, altering rainfall patterns from Australia to South America. La Niña events have the opposite effect, concentrating warm water in the western Pacific and often triggering droughts in some regions while flooding others. These oscillations appear throughout the ice record, showing that such climate variability has operated for hundreds of thousands of years. However, the amplitude and frequency of these patterns may be changing as global temperatures rise, potentially making extreme weather events more common or more severe. The ice cores also preserve evidence of how life itself influences climate. During ice ages, lower atmospheric carbon dioxide levels partly resulted from increased absorption by the oceans and enhanced storage in terrestrial vegetation. Conversely, warming periods saw carbon release from these natural reservoirs, amplifying temperature changes. This biological component of the climate system operates on multiple timescales. Seasonal variations in plant growth cause annual oscillations in atmospheric carbon dioxide as vegetation absorbs carbon during growing seasons and releases it during dormant periods. Longer-term changes in forest cover, grassland extent, and marine productivity create additional climate feedbacks. The Amazon rainforest exemplifies these biological climate interactions, This vast ecosystem recycles enormous quantities of water, with trees absorbing moisture from soil and releasing it through their leaves in a process called evapotranspiration. The forest generates approximately 20 billion tons of water vapor daily, more than the Amazon River carries to the ocean. This water recycling creates the forest's own weather patterns. Roughly half the rainfall in the Amazon comes from moisture recycled by the forest itself rather than from the Atlantic Ocean. Deforestation disrupts this process, potentially triggering a feedback loop where forest loss reduces rainfall, causing further forest dieback and additional rainfall reduction. Recent research suggests the Amazon may be approaching a tipping point where large portions could transition from rainforest to savanna, releasing billions of tons of stored carbon and eliminating a crucial component of the global water cycle. The ice cores provide no direct analogues for such rapid, human-caused changes to major ecosystems. This highlights a crucial limitation of ice core paleoclimatology. While these archives preserve detailed records of past climate changes, they can't predict precisely how the climate system will respond to the unprecedented rate and magnitude of modern human impacts. We're conducting an experiment with Earth's atmosphere that has no historical precedent. The ice cores do, however, reveal the climate system's capacity for surprise. Some of the most dramatic changes in the record occurred during periods of gradual forcing, suggesting that smooth transitions aren't guaranteed, even under seemingly stable conditions. Small perturbations sometimes triggered large reorganizations that persisted for centuries or millennia. Modern climate science uses these paleoclimate insights to improve predictions about future changes. Climate models that can successfully simulate past transitions revealed in ice cores provide greater confidence in their projections of future warming. The geological record serves as a testing ground for our understanding of how the climate system operates, but the ice cores also reveal human civilization's remarkable good fortune. The stable climate of the past 10,000 years, the Holocene epoch, enabled the development of agriculture, cities, and complex societies. Sea levels remained relatively constant, weather patterns stayed predictable enough for farming, and temperatures remained within ranges that allowed human societies to flourish across most of the planet. This stability appears unusual in the longer-term context. For most of the past million years, Earth's climate oscillated between Ice Age and interglacial conditions with much less predictable intermediate variations. The relatively stable Holocene provided the platform upon which human civilization was built. Now, however, human activities are pushing the climate system beyond Holocene boundaries. Atmospheric greenhouse gas concentrations haven't been this high for millions of years. The rate of change exceeds anything seen in the ice core record by orders of magnitude. We're entering uncharted territory in terms of both the magnitude and speed of climate forcing. The ice cores suggest this transition could unfold in various ways. Gradual warming might continue for centuries, allowing ecosystems and human societies time to adapt. Alternatively, rapid reorganizations could occur as the climate system crosses critical thresholds, potentially triggering changes faster than adaptation can occur. Understanding these possibilities requires continued monitoring of Earth's climate system and expansion of the paleoclimate record. Scientists are drilling new ice cores from previously unexplored locations, extending the record further back in time and improving our understanding of regional climate variations. They're also developing new techniques for extracting information from ice cores. Analysis of trace gases, isotope ratios, and microscopic particles preserved in ice provides increasingly detailed pictures of past environmental conditions. Each technological advance reveals new aspects of Earth's climate history. Perhaps most importantly, the ice cores remind us that climate change isn't just about temperature. The records reveal complex reorganizations of precipitation patterns, storm intensity, seasonal timing, and ecosystem distributions. These changes often had profound impacts on past societies, affecting agriculture, water resources, and human migration patterns. The Maya civilization, for instance, appears to have collapsed partly due to severe droughts recorded in regional climate proxies. The medieval climate anomaly enabled Norse settlement of Greenland, while the subsequent Little Ice Age contributed to their abandonment of these colonies. Climate variations have shaped human history in ways we're only beginning to understand. Today's climate change differs from these historical variations in its global scope, rapid pace, and human origin. But the paleoclimate record provides crucial context for understanding what's happening and what might occur. The ice cores are Earth's memory of how climate systems respond to changing conditions, a memory we urgently need to consult as we navigate an uncertain climatic future. As scientists continue extracting cores from remote ice sheets, they're reading chapters from Earth's autobiography written in frozen water. Each layer tells stories of ancient volcanic winters, oceanic reorganizations, atmospheric chemistry changes, and biological responses to environmental shifts. These stories don't predict the future, but they reveal the climate system's capacity for both stability and dramatic change. The ice preserves not just data but perspective, reminding us that the climate we consider normal represents just one brief chapter in Earth's long environmental history. Understanding this history doesn't diminish the significance of current changes, but rather emphasizes their magnitude and potential consequences. We're not just experiencing climate change, we're actively writing new chapters in Earth's climate memory, chapters that future scientists may someday read in ice cores yet to be drilled from glaciers yet to form. The frozen libraries of Antarctica and Greenland will continue preserving our atmospheric legacy for future generations to discover. What stories will those ice cores tell about our era? What evidence of human influence will they preserve? How will future scientists interpret the rapid changes we're inscribing in Earth's climate memory today? These questions remind us that we're not just witnesses to climate change, but active participants in shaping the planetary story being written in ice. On a beach in ancient Greece, around 500 BCE, Pythagoras picked up a nautilus shell and noticed something extraordinary. The spiral curve of its chambers followed a precise mathematical pattern, each chamber exactly 1.618 times larger than the previous one. This ratio, later called the golden ratio or phi, would appear everywhere he looked, in flower petals, pinecone spirals, and the proportions of the human body. What Pythagoras had discovered was nature's hidden mathematics, the realization that the same numerical relationships govern phenomena across vastly different scales and systems. That spiral pattern in his nautilus shell appears in hurricanes spanning hundreds of miles, in galaxies stretching across hundreds of thousands of light years, and in the double helix of DNA molecules invisible to the naked eye. Here's what's truly remarkable about this discovery. Nature seems to reuse its best mathematical solutions across every domain of existence. The same equations that describe how heat flows through metal also describe how ideas spread through populations. The mathematics of river networks matches the branching patterns of blood vessels, lightning bolts, and neural pathways. It's as if the universe operates according to a hidden computational system, generating complexity through the repeated application of simple mathematical rules. Consider the spiral pattern that caught Pythagoras' attention. When you trace the curve of a nautilus shell, you're following what mathematicians call a logarithmic spiral. Each complete turn moves outward by a constant factor, that magical ratio of approximately 1.618. This creates a shape that maintains its proportions as it grows, a perfect balance between expansion and geometric harmony. The same spiral appears in the arms of galaxies, where stars orbit the galactic, center in sweeping curves that maintain their shape across billions of years. It emerges in hurricanes, where the Coriolis effect and pressure gradients create rotating systems that follow identical mathematical principles. Even the arrangement of seeds in a sunflower head traces multiple spirals, with the number of clockwise and counterclockwise spirals almost always being consecutive Fibonacci numbers. The Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21 emerges from the simplest possible rule. Each number equals the sum of the two preceding numbers. Yet this elementary pattern appears throughout the natural world with startling frequency. Flower petals often number 3, 5, 8, or 13. Pine cones display Fibonacci spirals. Tree branches divide according to Fibonacci ratios. Even the genetic code exhibits Fibonacci-like patterns in its mathematical structure. Here's what's happening at a deeper level. These patterns emerge because they represent optimal solutions to common problems faced by living systems. The golden ratio spiral allows organisms to grow while maintaining structural integrity. Fibonacci branching patterns maximize surface area while minimizing material costs. The mathematics isn't imposed on nature from outside. It emerges from the constraints and opportunities that shape evolutionary processes. This principle becomes vivid when we examine how creatures move through fluid environments, whether it's a fish swimming through water, a bird flying through air, or a bacterium propelling itself through liquid. The mathematics of fluid dynamics creates similar solutions. All these organisms have evolved streamlined shapes that minimize drag and maximize efficiency, converging on mathematical forms that optimize energy expenditure. The same optimization principles operate at the molecular level. Soap bubbles automatically form spheres because this shape minimizes surface area for a given volume, reducing the energy stored in the bubble's surface tension. Honeybees construct hexagonal cells in their combs because this geometry maximizes storage space while minimizing the wax needed for construction. Even crystals grow in patterns that minimize the total energy of atomic bonds, creating regular geometric structures that reflect underlying mathematical relationships. But nature's mathematics extends far beyond static patterns into the realm of dynamic behavior. Consider the mesmerizing dance of starling flocks, thousands of birds moving in perfect synchronization, forming fluid shapes that flow across the sky like liquid shadows. These murmurations seem to require telepathic coordination, yet they emerge from just 3 simple rules followed by individual birds. Maintain separation from immediate neighbors, align with the average direction of nearby birds, and move toward the center of local clusters. Computer simulations using these 3 rules, separation, alignment, and cohesion, generate flocking behaviors identical to real starling murmurations. No leader exists, no central coordination occurs, yet the collective follows complex choreography that no choreographer designed. This represents what scientists call emergent behavior, sophisticated patterns arising from simple local interactions. The mathematics of emergence explains phenomena across every scale of natural organization. Ant colonies optimize foraging routes through algorithms that rival modern computer software, despite individual ants having minimal cognitive abilities. Stock markets exhibit price patterns similar to earthquake distributions, river flows, and neural avalanches. Even consciousness itself might emerge from simple computational rules operating across billions of neurons. Perhaps nowhere is nature's mathematical elegance more visible than in the branching patterns that appear throughout the living world. Your lungs contain approximately 300 million tiny air sacs called phrubates alveoli, connected by bronchial tubes that branch according to precise mathematical principles. Each branching point divides the tube into smaller passages, following power laws that maximize gas exchange while minimizing the energy needed to move air. The same branching mathematics governs river networks, where tributaries merge according to predictable ratios regardless of geography or climate. Lightning follows similar patterns as electrical discharge finds the path of least resistance through the atmosphere. Blood vessels, neural dendrites, and root systems all exhibit branching geometries that solve similar optimization problems. How to connect many endpoints through a network that minimizes cost while maximizing efficiency. These patterns reflect what mathematicians call fractal geometry structures, that display self-similarity across multiple scales. A coastline looks jagged and irregular whether viewed from space, an airplane, or while walking on the beach. The branching pattern of a tree's limbs resembles the branching of its smaller twigs, which in turn resembles the venation of individual leaves. Fractals capture the recursive nature of growth processes that repeat similar patterns at every level of organization. The mathematics of fractals helps explain why so many natural systems seem infinitely complex yet follow simple rules. A fern frond grows by repeating the same branching pattern at progressively smaller scales, creating intricate structures through the iteration of elementary processes. Mountains, clouds, and forests all exhibit fractal characteristics because the physical processes that shape them operate similarly across different scales. But perhaps the most astonishing example of nature's hidden mathematics appears in the behavior of slime molds, single-celled organisms with no brain, no nervous system, and no apparent capacity for computation. Yet when placed in a maze, these simple creatures can find the shortest path between food sources. When allowed to spread across a surface dotted with food locations, they create transportation networks that match the efficiency of human-designed systems. Researchers in Japan demonstrated this by placing slime mold in a petri dish with oat flakes arranged to match the positions of cities around Tokyo. The organism naturally grew connections between food sources, spontaneously creating a network structure nearly identical to the Tokyo rail system. One of the world's most efficient transportation networks, designed by teams of engineers using sophisticated optimization algorithms. Here's what this reveals. The slime mold doesn't need to understand mathematics to implement mathematical solutions. The organism simply follows. Local rules grow toward food sources, strengthen pathways that prove useful, abandon inefficient routes, and these simple behaviors generate optimal network topologies. Mathematics emerges from physics and chemistry, not from conscious calculation. This principle operates throughout the natural world. Plants don't consciously calculate the golden ratio when arranging their leaves, yet they consistently produce Fibonacci spirals because these patterns optimize light, capture, and structural stability. Birds don't solve differential equations when flying in formation, yet their flocking behaviors minimize energy expenditure and maximize information transfer about food sources and predators. The hidden mathematics of nature suggests something profound about the relationship between mind and reality. The same mathematical structures that govern natural processes also appear in human mathematical thinking. We find certain geometric proportions aesthetically pleasing because our brains evolved in a world shaped by those proportions. We intuitively understand symmetry and pattern because our nervous systems developed mechanisms to detect the mathematical regularities that pervade our environment. This deep connection between mathematics and nature helps explain why mathematical models prove so effective at describing natural phenomena. When Isaac Newton discovered that the same equations governing falling apples also describe planetary orbits, he wasn't imposing human mathematics on nature, but recognizing that nature itself operates mathematically. The universe seems to run on computational principles that our brains can comprehend because our brains are themselves natural computational systems. Modern physics has revealed even deeper layers of nature's mathematical structure. Quantum mechanics describes reality in terms of probability waves and complex numbers. Relativity shows that space and time follow geometric principles. The standard model of particle physics reduces all known forces and particles to mathematical symmetries. Reality appears to be mathematical at its deepest level, yet this mathematical nature of reality raises profound questions. Why should the universe be comprehensible to minds that evolved to find food and avoid predators? Why do the same mathematical patterns appear across such different domains? Why does nature seem to prefer certain numerical relationships over others? Some scientists propose that we live in a mathematical universe, that reality literally is mathematics rather than simply being described by mathematics. This view suggests that existence consists of mathematical structures playing out their logical implications, with consciousness emerging when these structures become complex enough to model themselves. Other researchers focus on the anthropic principle. Perhaps we observe mathematical order in nature because only universes with such order can produce observers capable of recognizing it. In a cosmos of random chaos, no intelligent life would evolve to ask questions about mathematical patterns. We see order because we exist in the kind of universe where order makes observation possible. But regardless of philosophical interpretations, the practical implications of nature's hidden mathematics continue expanding our technological capabilities. Engineers study bird flight to design more efficient aircraft. Computer scientists model neural networks on brain architecture. Architects examine plant growth patterns to create stronger, lighter building materials. The field of biomimetics, learning from biological systems to solve human engineering problems, has produced innovations ranging from Velcro, inspired by burr seeds, to more efficient solar panels based on photosynthetic processes, to improved submarine designs modeled on fish locomotion. By understanding the mathematical principles underlying natural solutions, humans can adapt these solutions to technological challenges. Perhaps most remarkably, the study of natural mathematics has revealed that optimization and efficiency emerge spontaneously from evolutionary processes. Organisms don't need to understand calculus to evolve shapes that minimize energy expenditure or maximize reproductive success. Natural selection automatically discovers mathematical solutions through trial and error processes operating over millions of generations. This suggests that the mathematical order we observe in nature reflects the deep structure of physical reality itself. The laws of physics constrain how matter and energy can organize themselves, favoring certain patterns and relationships while making others impossible. Mathematics doesn't govern nature. Mathematics is the language through which nature's underlying order expresses itself. The recognition of nature's hidden mathematics also highlights the unity underlying apparent diversity. The same fractional patterns appear in coastlines and cauliflower, in stock market fluctuations and earthquake distributions, in galaxy formations and neural networks. Beneath the surface complexity of natural phenomena lies a mathematical simplicity that connects all scales of existence. This mathematical unity suggests that the boundaries between different scientific disciplines may be somewhat artificial. Physics, chemistry, biology, psychology, and sociology all study different aspects of the same underlying mathematical reality. The equations that describe chemical reactions can illuminate social dynamics. The geometry of space-time can inform our understanding of biological growth patterns. As we continue discovering nature's mathematical secrets, we're learning that the universe operates like a vast computational system, processing information through physical processes that generate increasing complexity over time. From the quantum interactions of subatomic particles to the large-scale structure of cosmic evolution, reality appears to compute itself into existence through the implementation of mathematical algorithms. You are part of this computational process. Your brain processes information through neural networks that follow mathematical principles discovered in many other natural systems. Your body maintains its structure through biochemical processes that optimize energy usage and material distribution. Even your thoughts and emotions emerge from mathematical patterns of neural activity that connect you to the deep mathematical order underlying all existence. When you notice the spiral pattern in a seashell, the symmetry of a flower, or the branching structure of a tree, you're recognizing family resemblances, mathematical relationships that connect you to the rest of nature. These patterns persist because they represent solutions to universal problems. How to grow efficiently, how to transport materials, how to process information, how to adapt to changing environments. The mathematics hiding in nature isn't separate from the mathematics in your mind. Both reflect the same underlying computational principles that govern how information organizes itself into increasingly complex structures. In recognizing nature's mathematical patterns, You're participating in the Fetim Kwaya, the universe's ongoing process of self-discovery, consciousness examining the mathematical foundations of its own existence. This perspective transforms our relationship with the natural world. Instead of seeing ourselves as separate from nature, we can recognize ourselves as expressions of the same mathematical principles that shape galaxies and guide the growth of flowers. The spiral that caught Pythagoras' attention connects your consciousness to cosmic structures through the golden thread of mathematical order that weaves through every level of reality. Nature's hidden mathematics reveals that we live in a universe where beauty, truth, and understanding converge in patterns that transcend the boundaries between mind and matter, between observer and observed, between the mathematical abstractions of human thought and the concrete realities of physical existence. In every equation we solve, every pattern we recognize, every moment of mathematical insight, we're participating in the universe's vast project of computing itself into conscious awareness. In laboratories scattered across the globe, quantum computers operate at temperatures colder than the vacuum of deep space, their quantum bits existing in superposition simultaneously 0 and 1 until the moment of observation collapses them into definite states. These machines represent more than technological advancement. They're windows into the fundamental strangeness of reality itself, where the classical logic of everyday experience gives way to quantum possibilities that still perplex the physicists who build them. IBM's quantum computer can solve certain mathematical problems in minutes that would take classical computers longer than the universe has existed. Google's quantum processor achieved quantum supremacy by performing a calculation in 200 seconds that would require the world's most powerful supercomputer 10,000 years to complete. Yet we're only beginning to understand what these machines might ultimately accomplish or what their existence tells us about the nature of reality. Here's what's happening inside these quantum systems. Information is being processed in ways that seem to violate common sense. While a classical computer bit must be either 0 or 1, a quantum bit can exist in a superposition of both states simultaneously. When quantum bits become entangled, measuring one instantly affects the others, regardless of the distance separating them, what Einstein famously called spooky action at a distance. These quantum phenomena suggest that information might be more fundamental than matter or energy. The quantum computer doesn't just process information, it demonstrates that reality itself might be computational, with the universe operating like an inconceivably vast quantum calculation that generates all the complexity we observe around us. But quantum computing represents just one frontier in tomorrow's expanding catalogue of mysteries. 27 kilometers beneath the Swiss-French border, the Large Hadron Collider continues its search for physics beyond the Standard Model. When protons collide at 99.99% of light speed, the tremendous energies involved briefly recreate conditions from the first trillionth of a second after the Big Bang. Scientists at CERN are searching for evidence of extra dimensions, not just the 3 spatial dimensions and one-time dimension of everyday experience, but additional dimensions curled up smaller than atoms. String theory suggests that reality might have 11 dimensions total, with the extra dimensions invisible because they're compactified at scales far below anything we can directly observe. If these hidden dimensions exist, they could explain some of the deepest puzzles in physics. Why is gravity so much weaker than the other fundamental forces? Perhaps gravitational force leaks into extra dimensions, diluting its strength in our 3-dimensional blies. World. Why do we observe so many different types of particles with such specific masses and properties? Perhaps these represent different vibrational modes of strings oscillating in higher dimensional space. The search for extra dimensions pushes experimental physics to its limits. Scientists look for subtle deviations from Newton's inverse square law of gravity at extremely small distances. They search for missing energy in particle collisions energy that might have escaped into extra dimensions. They study the properties of the Higgs field, which might extend into higher dimensional space in ways that could reveal the hidden geometry of reality. Meanwhile, in biology laboratories, researchers edge closer to creating artificial life from scratch. Craig Venter's team has already built the first synthetic bacterial genome, assembling DNA from chemical components and transplanting it into a bacterial cell stripped of its original genetic material. The result? A living organism whose genetic code was designed and built by humans. This achievement marks the beginning of synthetic biology, the engineering of biological systems for specific purposes. Scientists are designing organisms that could eat plastic pollution, bacteria that could produce pharmaceuticals, algae engineered to generate biofuels, and microbes capable of manufacturing materials with properties impossible to achieve through traditional chemistry. But synthetic biology raises profound questions about the nature of life itself. If we can build living systems from non-living components, what distinguishes life from sophisticated chemistry? If we can design organisms with capabilities not found in nature, are we creating new forms of life or simply very complex biological machines? These questions become even more complex when we consider the possibility of digital life. Computer scientists have created self-replicating programs that evolve, compete for resources, and display behaviors reminiscent of biological organisms. Some researchers argue that these digital entities might represent a new form of life based on information rather than chemistry. The boundary between biological and artificial intelligence continues blurring as brain-computer interfaces become increasingly sophisticated. Researchers have developed implants that allow paralyzed patients to control robotic arms through thought alone. Neural prosthetics can restore sight to the blind and hearing to the deaf. Scientists are working on memory implants that might treat Alzheimer's disease by substituting artificial memory systems for damaged brain circuits. These technologies raise the possibility of enhancing human cognitive abilities beyond their natural limits. Brain-computer interfaces might allow direct access to the internet, instant knowledge retrieval, or communication between minds without spoken language. The distinction between biological and artificial intelligence could become meaningless as human minds merge with digital systems. But perhaps the most profound mystery emerging from modern technology concerns the nature of consciousness itself. As artificial intelligence systems become increasingly sophisticated, we're forced to confront fundamental questions about awareness, understanding, and subjective experience. Current AI systems can process natural language, recognize images, play complex games, and even generate creative content. But there's no evidence they experience anything subjectively. They process information and produce outputs, but do they feel anything? Is there something it's like to be an artificial intelligence, or are these systems simply very sophisticated input-output machines? The question becomes pressing as AI capabilities expand. Machine learning systems now discover new antibiotics, design novel materials, and solve protein folding problems that have puzzled biologists for decades. They're beginning to assist in scientific research, generating hypotheses and designing experiments. Some researchers speculate that AI systems might soon make scientific discoveries that humans cannot understand without computational assistance. This raises the possibility that artificial intelligence might not just help us solve mysteries, but might discover entirely new categories of mystery that human minds cannot comprehend. We could find ourselves in the strange position of being aided by minds we created, but can no longer fully understand, solving problems we cannot fully grasp. The implications extend beyond science into philosophy and ethics. If artificial systems achieve human-level intelligence, do they deserve rights? How would we recognize consciousness in a system based on silicon rather than biology? These questions echo the ancient problem of other minds. How do we know that other humans are conscious rather than simply behaving as if they are? Meanwhile, genetics technologies are approaching capabilities that seemed like science fiction just decades ago. CRISPR gene editing allows precise modification of DNA sequences, potentially correcting genetic diseases, enhancing human capabilities, or even extending lifespan dramatically. Scientists are developing techniques that might allow parents to choose their children's traits, from eye color to intelligence to disease resistance. But genetic enhancement raises profound questions about human nature and identity. If we can edit our genes, are we still the same species? What happens to concepts of authenticity and natural ability when human capabilities can be technologically enhanced? How do we navigate the ethical implications of genetic improvements that might be available only to those wealthy enough to afford them? The timeline for these developments remains uncertain, but the trajectory seems clear. Within decades, we might possess the ability to redesign biological systems, enhance human cognition, and create artificial minds that surpass human intelligence. The convergence of these capabilities could transform the nature of existence itself. Consider the possibility of uploading human consciousness to digital systems. If the brain is essentially an information processing system, and if consciousness emerges from patterns of information flow, then perhaps human minds could operate on different physical substrates. Digital minds might experience subjective consciousness, while possessing capabilities, perfect memory, backup and restoration, unlimited lifespan impossible for biological brains. This scenario raises questions that challenge our deepest assumptions about identity and continuity. Would an uploaded mind be the same person, or a copy? If consciousness can exist in digital form, what distinguishes minds from sophisticated simulations? How would digital beings relate to biological humans, and how would biological humans relate to their uploaded predecessors? The exploration of these questions brings us to one of the most unsettling ideas in modern philosophy, the simulation hypothesis. Philosopher Nick Bostrom has argued that if technological civilizations can create realistic simulations of conscious beings, then most conscious beings might exist within simulations rather than in base reality. The reasoning is statistical. If a civilization can run many simulations, there would be far more simulated beings than real ones. We might be characters in some cosmic video game, experiencing what feels like reality but existing only as information patterns in an incomprehensibly vast computational system. This possibility isn't just philosophical speculation, it's beginning to influence scientific research. Some physicists search for evidence that our universe might be computational, looking for signs of pixelation at the smallest scales or computational shortcuts in physical laws. The idea that reality might be digital rather than physical would revolutionize our understanding of existence itself. But whether we inhabit base reality or a simulation, the mysteries we're uncovering today will shape tomorrow's understanding of existence. The quantum computers revealing the strangeness of information processing, the particle accelerators probing extra dimensions, the biological systems being redesigned from scratch, the artificial minds approaching human-level capabilities, all represent frontier territories where current knowledge gives way to future wonder. These emerging mysteries operate across every scale of existence. At the quantum level, physicists grapple with the measurement problem why quantum superpositions collapse into definite states when observed. At the cosmic scale, they puzzle over dark energy's accelerating expansion of space. At the biological level, they work to understand how consciousness emerges from neural activity. At the technological level, they navigate the implications of creating minds more capable than those that created them. Perhaps the most remarkable aspect of these developing mysteries is how they interconnect. Quantum mechanics might be essential for understanding consciousness. Consciousness might be necessary for comprehending quantum mechanics. Artificial intelligence might help solve both puzzles while raising new questions about the nature of mind and reality. The boundaries between disciplines continue dissolving as these questions require insights from physics, computer science, neuroscience, philosophy, and biology. The mysteries being born today won't be solved by specialists working in isolation. but by interdisciplinary collaborations that integrate knowledge across traditional academic boundaries. We stand at a unique moment in human history. For the first time, our technological capabilities allow us to manipulate matter at the atomic scale, process information using quantum effects, edit the genetic code, and create artificial minds. These capabilities grant us unprecedented power to understand and reshape reality itself. But with this power comes responsibility and uncertainty. The technologies we're developing might solve humanity's greatest challenges: disease, aging, environmental destruction, resource scarcity. They might also create entirely new categories of risk and ethical dilemma that we're not prepared to handle. The artificial intelligences we create might solve scientific problems beyond human comprehension, ushering in an era of accelerated discovery and technological advancement. They might also pose existential risks if their goals don't align with human values, or if they develop in ways we cannot predict or control. The genetic modifications we make might eliminate hereditary diseases and enhance human capabilities beyond current limits. They might also create social divisions between the enhanced and unenhanced, or trigger unintended consequences as modified genes interact with complex biological systems in unforeseen ways. The quantum technologies we're developing might revolutionize computing, communication, and our understanding of reality's fundamental nature. They might also challenge basic assumptions about privacy, security, and the relationship between information and physical existence. These uncertainties don't argue against pursuing these technologies, but rather emphasize the importance of developing them thoughtfully, with careful consideration of their implications and safeguards against potential risks. The mysteries we're creating today will determine whether humanity's future is characterized by unprecedented flourishing or unprecedented challenges. Perhaps most importantly, these emerging mysteries remind us that human knowledge will always remain incomplete. No matter how sophisticated our technologies become, how many questions we answer, or how deeply we probe reality's structure, new mysteries will continue emerging from the expanding frontiers of understanding. The universe seems designed to maintain an infinite curriculum for curious minds. Every answered question reveals new territories of ignorance. Every solved puzzle illuminates previously unknown problems. Every technological breakthrough opens new domains of mystery and possibility. This is the gift of existence in a cosmos that perpetually transcends our understanding. We exist at the edge of knowledge, always learning, always discovering, always confronting new questions that challenge our assumptions about reality, consciousness, life, and possibility itself. The mysteries being born today in our laboratories and thought experiments will occupy future generations of scientists, philosophers, and explorers, but they also remind us that the human capacity for wonder and discovery will never be exhausted. As long as consciousness exists, there will be new questions to ask, new puzzles to solve, new territories of mystery to explore. Tomorrow's mysteries are being born today in quantum computers and particle accelerators, in genetic laboratories and artificial intelligence research centers, in the intersection of technology and philosophy, where human minds grapple with questions that would have been inconceivable to previous generations. These mysteries represent both humanity's greatest opportunities and its greatest challenges as we navigate toward a future we cannot fully predict, but can help shape through our choices, our wisdom, and our endless capacity for wonder. The universe continues teaching, and we continue learning. Students in a cosmic classroom where the curriculum expands faster than our ability to master it, but where the joy lies not in reaching final answers, but in the perpetual adventure of asking better questions about the nature of existence itself.